Thank you very much for the kind introduction, and thanks everybody for joining our webcast today. This is the agenda for the next 45 minutes. I will start with a comment on why higher data rates are needed, and then compare the different technology options which can roughly be categorized in direct detection and coherent detection. It turns out that coherent data transmission technologies will be used for shorter and shorter distances as the data rates increase. I will therefore focus on coherent transmission technologies for the remainder of this webcast and talk about the options for increasing the data rates and discuss the respective requirements. My colleague Mike will then introduce the next generation high bandwidth oscilloscope and talk about the technology innovation that was required to achieve this. This new technology will allow you to analyze signals that were not possible to be analyzed before. In the last section, I will provide some example measurements to prove this claim. I will show that together with our new 120 gigasamples per second arbitrary waveform generator, we can increase the symbol rate to 100 gigabaud. Now, let's get started with a short comment on the increasing internet traffic, which is driven by applications like video streaming, as well as increased number of connected devices. As you can see from the study here offered by the company Cisco, the internet and data center traffic is expected to grow at about 24 to 25% each year, and the saturation of that growth is not yet in sight. This requires a continuous scaling of the underlying data center interconnects as well as metro and long-haul networks using higher speed transceivers. So those application spaces are summarized here together with the typical link distances in the respective areas. At the bottom of the slide, I want to highlight the typical technologies used, which is coherent for the long distance and direct detection where NRC and PAM4 modulation schemes are used for the short distances. It's a big debate at what distance does the technology transition between coherent and direct detection happen. It turns out that this transition is moving to shorter and shorter distances as the data rates go up. This can be understood when considering that for direct detection technologies, it becomes more and more difficult to transmit over long distances as the data rates go up, while coherent technologies, they can be simplified when designing them for specifically for short reach applications. So this is also illustrated in the graph here from Acacia that you can see on the left-hand side. On the right-hand side, you can see a summary of the trade-offs between direct detection and coherent technology. Direct detection typically has advantages in terms of cost, power, size, and latency. However, those advantages become smaller once the distance requirements increase, and then they require, for example, additional chromatic dispersion compensation. Furthermore, in a dense wavelength division multiplexing network, there is only a limited spectral efficiency that can be achieved. So this limits the overall capacity to around 4 terabit per second in the C-band. On the other hand, coherent technologies are typically expensive, power-hungry, and do not fit into small form factors. But this can be addressed by moving to smaller CMOS nodes, as well as by the reduced requirements on the DSP for short-reach applications, such as there's no more chromatic, or there's less requirements on the chromatic dispersion compensation, for example. Also, in a dense WDM network, higher capacities can be achieved, and the capacity can scale in the future by moving to higher order QAM signaling. So going back to the graph on the left-hand side, a possible scenario could be that for data rates at 400 gig, the transition happens at around 10 kilometers, while looking further out towards 800 gigs, the transition might already be at as low as 2 kilometers. So in the remainder of this webcast, I want to focus on the coherent transmission technologies and discuss the challenges when moving to terabit per second transceivers. We will show how the latest innovations in test and measurement technology can help you accelerate your project. To get started, I want to recommend our new white paper on the fundamentals of coherent optical data transmission. You can find this white paper also in the resource list of this webcast. We explain there all the basics, starting from modulation formats, pulse shaping techniques, and how complex modulation formats are being generated. We then explain in depth the coherent receiver and how the signals can be analyzed along with the respective quality metrics and impairment analysis. In order to determine the data rate for a coherent transceiver, you need to take into account the following parameters: the symbol rate, the constellation size, which sets the number of bits carried by each symbol, and the number of carriers. The latest technology that is available on the market is transmitting a net data rate of 1.2 terabit per second, and it is using 64 QAM at 64 gigabaud with 2 carriers. You can also see this in the first item on the table on the lower right-hand side. While this technology certainly has the advantage of being early to market, it's available now, it is expected that mainstream terabit transceiver will move to a single carrier solution and scale on symbol rate and or constellation in order to reduce the cost. The table on the bottom right shows a collection of research records where above 100 gigabaud symbol rates have been achieved. In the following slides, I want to shed some light on the requirements for scaling both symbol rate and constellation. I will show that for 100 gigabaud, a bandwidth in excess of 50 gigahertz is required, and that for 64 QAM, above 5-bit ENOP is desired. So first, let's have a look at the bandwidth requirement. This depends on the symbol rate and time domain pulse shaping. The top picture shows the spectrum of the signal without any filtering. In this case, the signal spectrum theoretically extends infinitely with null points at each integer multiple of the symbol rate. Taking just the main lobe into account, a bandwidth of 2 times the symbol rate is required, centered around the carrier. After optical to electrical conversion, the required RF bandwidth corresponds to the symbol rate. Assuming a symbol rate of 100 gigabaud, so the required bandwidth of the electrical and electro-optical components would be 100 gigahertz. With raised cosine filtering and a filter alpha of 1, the signal spectrum is fully concentrated within a bandwidth of 2 times the symbol rate. There are no side lobes in the spectrum anymore. The bandwidth requirement for the components corresponds exactly to the symbol rate in this case. It is possible to further reduce the bandwidth requirement by up to a factor of 2 when using smaller filter roll-offs, as shown in the 2 bottom pictures, for roll-off of 0.35 and 0.05. Theoretically, data transmission is possible within an RF bandwidth of half the symbol rate, which would correspond to 50 gigahertz for 100 gigabaud signals. But in practice, signals become more difficult to demodulate if small roll-off factors are used. So typical roll-off factors you can find in coherent transmission systems today are of the order of 0.2 or higher. At the receiver part, I also want to mention that some excess bandwidth is required to account for frequency offset between carrier and local oscillator in case intradyne detection is used. So to summarize again, more than 50 gigahertz is needed, and the more the better if you want to go to 100 gigabaud. Next, let's have a look into scaling the constellation order. In the table on the left-hand side, the number of bits per symbol increases for each line from 1 to 10. The second column shows the respective modulation format, and the third column gives the minimum required symbol rate to achieve a 1 terabit per second transmission with the given constellation. That means without considering any overhead, which is typically dominated by the forward error correction and is of the order of about 20 to 30%. So taking into account the HERO experiments where about 100 gigabaud and slightly above symbol rates have been achieved, this would mean that a modulation format of 32 QAM or higher would be needed for terabit per second transceivers. On the right-hand side, you can see typical constellation diagrams for some of the mentioned modulation formats, and underneath the graph showing the number of symbols in a constellation diagram versus the number of bits per symbol. It can be seen that over proportionally more points need to be added to a constellation diagram when increasing the number of bits per symbol. With an increasing number of constellation points, the Euclidean distance between the points decreases, and this makes the transmission more susceptible to noise. Or in other words, the requirements on the signal-to-noise ratio increase. This translates also into the requirements on the noise of the underlying digital-to-analog and analog-to-digital converters. This is typically expressed using the ENOP, effective number of bits. In the table you can see here, I have compiled ENOP numbers that are evaluated in the literature. All of them take slightly different metrics, but in principle, they evaluate the SNR penalty at a given bit error ratio for various ENOP numbers, and then report the lowest ENOP that ensures a SNR penalty below a certain threshold. You can see the applied metric in the second line of the table. The table shows that the ENOP requirement roughly increases by 1 bit for each incremental bit per symbol in the modulation format. Secondly, you can see that the ADC seem to have tighter ENOP requirements than the DAC. Taking a look at 64QAM, the ENOP requirement is below 5 bit for the DAC and somewhere between 5 and 6 bit for the ADC. Having those requirements in mind, let us take a look at what the current state-of-the-art test equipment can deliver in terms of performance when doing a back-to-back experiment, generating signals at 64 gigabaud using our optical modulation generator software. You can see a screenshot on the lower left-hand side, and our arbitrary waveform generator running at 92 gigasamples per second. This is the black box in the middle, with a bandwidth of more than 32 gigahertz and an ENOP of more than 5 bits. An optical multi-format transmitter, this is the green and gray box underneath the AWG. This has more than 40 gigahertz bandwidth and is used as the electrical to optical converter. The receiver is an optical modulation analyzer built with two C-series oscilloscopes that are synchronized to get 4 channels at 160 gigasamples per second with 63 gigahertz of bandwidth and an ENOP of typically 4.5 bits. On the right-hand side, you can see the constellation diagrams for 16QAM and 64QAM at 64 gigabaud and the measured error vector magnitude as well as the measured bit error ratio. Looking particularly at the 64QAM constellation, there is no margin in the system for evaluating components or for doing transmission experiments. And I would like to highlight that this test equipment still represents the best signal integrity and lowest noise floor that is available on the market right now. I would also like to highlight that experiments at 64 gigabaud 64QAM were still possible with those instruments, but they required some more sophisticated signal processing techniques on both the transmitter and the receiver side. But nevertheless, scaling that to 100 gigabaud will require innovation on all the fronts. It will require higher sampling rates, higher bandwidth, and better ENOP. I will now hand over to Mike to go into more detail for the technology innovation on the oscilloscope.
Thanks, Jörg. So yeah, let's recap what's necessary then to have an oscilloscope capture the signals necessary to drive us past a terabit per second in coherent optical transmission. What are those oscilloscope needs? So first, we need 4 channels of simultaneous acquisition, real-time, in order to implement and test those DSP algorithms that recover symbol clocks and remove impairments and shape pulses. As you can see, right, we split the signal into horizontal and vertical polarizations, and then we do IQ demod on those signals. So therefore, you can see on the right, we need 4 channels of real-time oscilloscopes. We also need that acquisition at greater than 70 gigahertz of bandwidth to capture these extremely high baud rates signals. And we also need better signal integrity, i.e. better signal to noise ratio and better distortion to capture the higher order modulation signals. And we sum that up in saying that the oscilloscope needs to have better than 5 effective number of bits to be able to handle a QAM64 signal. Again, effective number of bits is really simply a log 2 expression of your signal to noise and distortion. So lower noise, lower distortion equals better signal integrity, equals the ability to discern the different constellation points from each other, and the ability to cover higher order modulation. So in order to address these needs, Keysight's introducing the new UXR series oscilloscopes with real-time bandwidth on 4 channels up to 110 gigahertz. again, available in 80, 100, and 110 gigahertz models. But the key thing here is that for the first time, we have these high bandwidths available on such wide bandwidths necessary for these acquisitions. Again, that real-time acquisition on all 4 channels is enabled by a 256 gigasample per second sample rate on all 4 channels with up to 2 gigapoints of memory, so you can capture the many milliseconds of data necessary to implement these DSP algorithms that are tracking and removing dispersions and other impairments. We also have, it's based on our new 10-bit ADC technology. Again, that's key to accomplishing the effective number of bits and displaying and demodulating these higher order constellations, ability to look at a wide variety of signals, and available in 2 or 4 channel models. And also we'll talk a little bit about the self-calibration module available for this product. Okay. So before I talk about the technology necessary to implement this new oscilloscope, I want to look back in time a little bit and look at our previous generation of oscilloscopes that went up to 63 gigahertz. And we were able to accomplish this by having a front end that used frequency splitting, where we split the signal into a high and low band and then ran it into 2 existing 33 gigahertz channels. And we're able then stitch those frequency components back together and get a 63 gigahertz channel. There's a couple of problems with that. It leads to some spurious issues that limit our ENOB, as well as it limits our noise because we are doing analog signal processing before we hit our preamplifiers. And so obviously for best noise performance, we want to have our preamplifiers out in front of that analog signal processing, that analog frequency domain split. So here we have the block diagram of the new UXR oscilloscope. It has right out in front an attenuator followed by a preamp and then followed by a sampler that samples that has 110 gigahertz of bandwidth and processes the analog signal into 256 gigasample distinct samples that are then sampled again by a second rank of sampler that breaks it down into 16 gigasample per second analog samples that are then digitized by the A to D converter. So it's this process of time interleave sampling that allows us to keep the signals and circuits small, keep the losses down, and keep the signal integrity high. These very fastest preamps and samplers are implemented in Keysight's proprietary indium phosphide process. And if I talk a little bit for a second about indium phosphide, it's a real test and measurement workhorse for Keysight. We're developing these transistors because of the not only the extremely high speed, but the high gain and high voltage handling capability of these 3.5 transistors. In comparison to other technologies, it's that high voltage, high gain, and high speed capability that together give us the distortion and signal to noise ratio capabilities that enable the 5 effective bits plus that enable us to then demodulate signals up to QAM 64 signals all the way up to the baud rates necessary to support Terabit Ethernet. Let's take a look at what the technology actually looks like here. Here we see a blown up picture of our front end module that's based on technology we call high board technology that allows us to launch a signal at 110 gigahertz onto the ASICs that are carried by this gold frame and thin films to distribute the signal as it is sampled first at 256 gigasamples and then at 64 gigasamples and gets us down to a frequency that can be then handled by the PC board technology and the A to D converters. So again, all the custom samplers, custom preamps enable us to keep the signals small, which limits loss and improves our signal-to-noise ratio, but also allows us to get the 4 channels that are necessary for the coherent demodulation in a single oscilloscope. So once the signal leaves this acquisition module, it comes in and goes into a much larger acquisition board where the signal is digitized and then processed and stored into 3D memory. It's this new memory interface in the middle here that allows us to handle the 256 gigasamples across 4 channels at 10 bits each. Means that we have to handle 10 terabits per second. So not only do we need good signal-to-noise ratio and good distortion, but we need flat phase and frequency response for our for effective demodulation of these signals as well. And we achieve that with a new calibrator. Again, the calibrator has a indium phosphide amplifier that generates a very, very fast step that has frequency content all the way out to 140 gigahertz. Not only is it a very fast step that has a large amount of frequency content, but it is a calibrated step generator in the sense that we have, in a traceable way, captured the frequency content in both magnitude and phase and stored it with the calibrator. So we start with traceable impulse generators, photodiodes from the National Standards Laboratories, and then we calibrate sampling scopes with those pulses, and then we measure these calibrators with those sampling scopes, and if then generated a traceable standard here in both magnitude and phase out to 110 gigahertz. So this allows you then to do the adjustments of the oscilloscope on site the exact same way we do in the factory. I do want to add one footnote here down at the bottom. It says that this is, this is the exact same frame calibration that we do in the factory, but it doesn't do the second half of calibration, which is bringing up different equipment to independently verify then that you have met your warranted specs and issue a certificate of conformance. Getting that certificate of conformance still requires a return to factory calibration. Okay, so if I take a step back then and look at the entire product line that the UXR enables, it's products from 13 gigahertz all the way up to 110 gigahertz, all with very low jitter, very low noise, and effective number of bits high enough to support higher order demodulation. If we look at some key measurements, here we taking some measurements on 4-channel 110 gigahertz oscilloscopes. In the upper left, we see the frequency response, calibrated frequency response, out past very flat, out past 100 gigahertz. In the upper right, we see an effective number of bits measurement that's well north of 5 bits, and very flat with frequency all the way out to 110 gigahertz. So what a flat effective number of bits means is that our measurement is limited by noise. Remember, effective number of bits is an expression of your signal to noise and distortion ratio. So here we're seeing a very flat enom versus frequency. That means that our measurement is, in almost all cases, limited by noise and not distortion. Please ignore the dips in the measurement right around the bandwidth of the oscilloscope. Note that those are at 112 gigahertz and above, so outside of the range of the oscilloscope, and we have some bunnies in the measurement. Below are different expressions of noise as a percentage of full scale, but in general, we're seeing a good 4 to 6 dB improvement of noise density over our previous generation oscilloscopes. So with that, I'll turn it back to Jorg, and he'll talk about some example optical measurements.
Yeah, thanks, Mike. So after I've quickly introduced the hardware to generate coherent optical data signals in the first section of the webcast, I want to go into a bit more detail on this now. The reference coherent transmitter starts with a software to mimic the transmitter DSP, and in that case, we offer our optical modulation generator tools, which has a large selection of standard modulation formats included, and generates the associated dual polarization IQ signals. It allows to set up the pulse shaping parameters to apply frequency response de-embedding through S parameters or other methods, and it's possible to intentionally impair the signals in a deterministic way to emulate effects like laser phase noise, polarization, rotation, PMD, and nonlinear transfer function. The software then connects to our arbitrary waveform generators, where we offer 4 independent analog outputs ideally suited for dual polarization IQ signals, and we have a selection of high-speed arbitrary waveform generators. And just this month, we actually added a new member to our AWG portfolio. This is the M8194A, which operates at up to 120 gigasamples per second and allows signal generation at more than 50 gigahertz with an analog 3 dB bandwidth of more than 45 gigahertz. As a last element, the signal needs to be modulated onto an optical carrier using an EO converter, as for example the optical multi-format transmitter offered by ID Photonics. This box contains a dual polarization IQ modulator with the necessary linear RF driver amplifiers, as well as a pattern-independent bias controller. I want to show a few more details on the brand new arbitrary waveform generator, and here to the left you can see a typical frequency response of the AWG output. There's a little highlight in the slide there that shows you that at 45 gigahertz there's a rough attenuation of about 2.5 dB, and even at 50 gigahertz the loss is only about 7.5 dB. So this can still be compensated for by pre-distorting the waveform, which makes it feasible then to use that to generate 100 gigabaud signals using that AWG. On the right-hand side, you can see an E-knob measurement over frequency, and also here you can see that this is between 5 and 6 across the whole frequency range. And later in this webcast, you will see some results obtained with this arbitrary waveform generator that go up to 100 gigabaud signals, and this gives you a first impression of what can be achieved with this new instrument. Before that, I want to also take a look at the reference receiver. And here we offer our portfolio of optical modulation analyzers. Those systems perform just the inverse operation of the aforementioned reference transmitter. So that means we start with an optical to electrical converter. This is a calibrated dual polarization coherent receiver, which can either be a box underneath the oscilloscope that you just got an in-depth introduction by Mike, or it can be an integrated version together with a 4-channel ADC that's located inside. We call that AXIE module. You see the black box on the upper right-hand side. And the last element of an optical modulation analyzer is the software platform that is used to recover and analyze the data signals. Here we follow the strategy of offering the very same software across our whole OMA portfolio, including our previous generations, to ensure that we have consistent analysis features and we can get comparable results across all the systems that we offer in our portfolio. Now, just one last thing before I move on to the measurements. I would also like to highlight a new feature for our optical modulation analyzers. So in order to avoid sending back the OMA to a factory for verification and recalibration, we also offer now an option to do this on site. The verification can check frequency response flatness, IQ angles, skews and gain imbalances, as well as verify image suppression and the error vector magnitude noise floor. And it can perform recalibration in case necessary of the mentioned parameters. So let's get to look into some actual measurements. In the first part, I want to show a comparison between the current and the next generation of optical modulation analyzer based on the new oscilloscope. So for that comparison, I'm using the current generation AWG. The other one wasn't available at the time when I did this measurement. So this is with 92 gigasamples per second AWG. And using the ID Photonics optical multi-format transmitter as the E12 converter. There's an EDFA and a filter in the setup. After that, the signal is split equally to the two optical modulation analyzers. So on the left-hand side, you can see the results for a 64 QAM and a 64 QAM, both at 64 gigabaud, using the prototype of our next generation OMA. And on the right-hand side, you can see the same signals measured with the current generation. And this is the same screenshots that you've seen earlier in this webcast for the current generation of our test equipment. So both visually and when you compare the numbers, you can see the improvement of the results. Particularly when you take a closer look at the bit error ratio, you can see that the number of errors is approximately dropping by a factor of 2. So this is consistent with the 1-bit ENOP improvement that we see between the new oscilloscope and the current one, which is also corresponding to a factor of 2 improvement. Secondly, I want to show you how far we can go with increasing the symbol rates for a given modulation format when using both the current generation AWG as well as the new one. In both cases, the signals are received and analyzed with the same OMA prototype as I showed you before. As a side note, I want to mention that I'm using different software interfaces for the current and for the new AWG. That's simply due to the fact that the OMG tool has not yet been updated to support the new AWG, at least at the times when I took those measurements. So some of the features that I typically use with the OMG software are not yet available in the measurements that I have here. So these measurements will have to be repeated once both the OMA system and also the AWG is actually moving to the final production quality. But here's the preliminary results that we can achieve already in this prototype status. And I show the results here in 2 plots. One is for single polarization signals and one is for dual polarization signals. Each plot shows the EVM over symbol rates for symbol rates going from 64 gigabaud all the way to 100 gigabaud. The modulation format is 16 QAM in all the cases, and the roll-off factor was adapted to lower values from 0.35 to 0.05 as the symbol rates were increased from 64 to 100 gigabaud. The orange curve shows the results for the current generation M8196A with up to 92 gigasamples per second, and the blue curve shows the results for the new AWG, the M8194A, with up to 120 gigasamples per second. The curves show an expected increase of the EVM with symbol rate. That's due to the fact that a lower SNR, that is due to the fact that we get a lower SNR as the symbol rates go up. So you can understand this when considering that the signal power is already maximized for the lowest symbol rate and therefore constant. But the noise power increases as the signal bandwidth increases, and since noise power density is assumed to be constant over frequency. So additionally to that, however, there is another contribution to increasing the EVM with symbol rate. As the symbol rates increase, we need to apply increasingly stronger preemphasis to the AWG waveform in order to overcome the frequency roll-off of both the AWG and even more the OMFT, which also starts to have a significant roll-off beyond 40 gigahertz. But still, nevertheless, this shows that we can go up to 100 gigabaud 16 QAM signals already now with the prototype hardware and software that we have here. And this would correspond to a line rate of 800 gigabit per second. We expect to see some further improvements once we move to the final hardware and software. So to summarize what we've discussed in our webcast today, we've discussed that in future, as transceiver speeds increase, the technology transitions from direct to coherent detections for shorter and shorter distance applications. Higher bandwidth and lower noise test equipment are crucial for development of components and systems for higher symbol rates and for larger constellation sizes, which are required to achieve also terabit per second transceivers in the future. With the new 120 gigasamples per second AWG and 256 gigasamples per second UXR-based optical modulation analyzer, you can have the next generation of the test equipment for the next generation optical transceivers and to develop those. So I would like to thank you all for following this webcast, and we will now proceed to the question and answer session.